Good morning, Cirencester College chemists. Okay, so we have started chapter 18, which is rates of reaction. It's a second year topic, and you've done the first section 18.1. So I'm now going to move on to looking at 18.2. Okay, so we'll go back to the start of that presentation. Okay, so let's go to. Okay, so we'll go to the start. Okay, so homework. Basically, everything you're doing pretty much is homework at the moment. Try and keep up with the booklet work, and the booklet is now on your OneNote for all the different classes, column A, C, D, and E, if I remember all the columns correctly. I'm going to be looking to the side a bit because the presentation is on the second screen, so it might look a bit odd if I'm looking in a different direction. Okay, but my screen is here. Okay, so what it says on there, all good. We're on Teams to help with questions. Your friends are on there as well. In the booklet there is a tick sheet. Well, there are tick sheets with all the lessons. So the lessons are either under lesson diary, class diaries, or year 2 lesson plans. And this week, what we've done is we've started with each lesson diary entry has started W/C, which stands for week commencing, and obviously yesterday was the 8th, so it's the 8th of the 6th of 2020. And I'm recording lesson 3 now, so this is the last lesson of the week that you should be doing, whichever day that is, either Thursday or Friday. Okay, so there are tick sheets, or there's a tick box that you can tick when you've done stuff on that tick sheet in OneNote, so it's always a nice thing to do to tick things off on your list. Okay. Also, in the booklet there is a tick list which we'd like you to sort of do on the booklet, which sort of says, you've done the stuff that's in there, you've covered the specification, because the tick list in the back of each of the chapter booklets is the specification. Really good to be aware of that. And you could either tick it off as you go along, or you could tick it off once you come to revise at the end, and you're revising and I'm sure of that. Also useful with things like a priority cross, which is a way of deciding what you should be revising. No point in revising stuff okay? Okay, so the booklets then, I'll talk a bit about the booklets later on, okay, and I'll show you some of those. Okay, also there's things online like ChemGuide, McChemGuide, Doc Brown's website, Snap Revise videos, which also are now doing live videos at about 5 to 3, I think it is, every day. But if you look on the Snap Revise YouTube site, they do live videos which you can actually put questions up, and those questions appear live on the video and they get answered at the same time. Okay, so last lesson, okay, what you need to do is see if you can remember what the shapes of the different graphs are for a 0 first and second order reaction. So there's this idea of orders of reactions. So see if you can do that. Okay, so for the moment, let me see where I've got to on my thing here. So stop the video now and see if you can remember the shapes of those graphs. Okay, so let's go on and see what they actually look like. So here we have them ready. Okay, so 0th order. So you're plotting concentration. The concentration, and in this case the concentration is dropping, so we're measuring the loss of the concentration of the reactants. So the concentration is dropping, and if 0th order, when the order is 0, then the concentration of that particular reactant is dropping constantly at a constant rate. Okay, and it could be that this reaction overall is 0 order. Okay, or it could be just one specific reactant. It could be 0 order for all reactants, okay? But it could be just one reactant that is 0 order. In the second graph, you've got the first order, which is a half-life curve. Okay, and we'll come on to that and look at that in a bit more depth a bit later on. And that means that the concentration starts off, it drops off very quickly, then gets a bit slower and a bit slower and a bit slower. And in second order, okay, it drops off very, very quickly, and then the rate starting to slow down. Okay, so you know the issue, as it says on the screen there, is that being able to judge the difference between, and I'm just going to change my screen a bit to make it a bit smaller so you can see everything on the graph. On the page. There we go. Okay, so the issue is that how do you tell the difference between a first and second order? I mean, you can see those ones are nice and clear, but sometimes they're a bit they're not quite so clear. Okay, so these are our learning objectives. We're going to plot these concentration time graphs from results from an experiment. We're also going to make sure we're continuing to understand how a continuous monitoring happens. We're going to deduce the rate of reaction from the concentration time graph. You should be able to work out a half-life from the first order graph, and you should be able to determine the rate constant from the half-lives. Okay, so I'll put that back up again for a second. So that's our learning objectives. Okay, so here, okay, are the main keywords which are on page 13 to 17 that you're going to come across in the booklet. So continuous monitoring of a reaction, using a colorimeter, which is a useful device to do that with, and the idea of half-life. So continuous monitoring, continuously taking measurements during the course so that you can see how the concentration is dropping as it goes through. So it's going to come start off, and you're going to be able to measure at different points along. Just trying to get my finger in the right place. Yeah, there. I've got this in reverse. So you start off here, high concentration of reactant. You can measure it there. You might measure at this point over here, this point over. Oh my God, this is hand-eye coordination there. Okay, so you're getting sort of, yeah, I'll do it in reverse. Ooh, no, I can't do it that way. I have to do it that way. Right. Okay, so you're getting this curve potentially, or a straight line. Half-life is time taken for the amount of a reactant to come down to half, so from like 10 to 5, and then from 5 to 2.5, and then from 2.5 to 1.25, etc. So you're going down by half the amount each time. And a colorimeter, be really careful how you spell that. Notice it's the American spelling of colour, but colour is as in colour rather than, you know, be careful, because with one change, if you stick an A in front, you get calorimeter, which measures heat, and this is a colorimeter. Okay, really important. And you need to pass light through the sample. Now this works if you've got a coloured sample or something that obscures the light as the reaction progresses. And you have to select your filter correctly. So for instance, if you have copper sulfate, which we all know is a blue colour, copper sulfate solution, a blue colour, what does that mean? That means it's absorbing all the colours, okay, except for blue light, and it's letting blue light through. Okay, so it's absorbing red and green. So what you need to do is select a filter to measure how much of the red light gets through. So if you have white light, you put it through a red filter, so you're shining red light through the filter, and you're detecting the red light at the end, or just shine white light and only detect the red at the other side. If it's stronger blue, that means it's absorbing more of the red light. So the absorbance will be much lower if it's a dark or more concentrated copper sulfate solution. Okay, so let's move on. Okay, perhaps biologists would have already used a colorimeter. Okay, so I'm going to give you a bit of time to think what changes occur during a reaction. Okay, so yeah, I will get you to. I'll just stop the video now and then just have a little think, and then we'll come back. Okay, so what changes can occur during a reaction, and how can we measure them? So hopefully you've thought of things such as pH, yeah, of a reaction, okay, and we can measure that in that way or in that way, i.e. we're using the change in the pH using a pH meter, okay, which is obviously at the top, and I think it was reading 4.16, or using titration, okay, so you can measure the change in that way, okay. You could measure the change in colour of a substance, okay, and that would be where our colorimeter comes along, okay. So there's various different models of colorimeter. You can see that up here we have got the cuvettes. Okay, now this is quite a nice one because it's got two cuvettes in at the same time. I think it's got a one which is going to be a blank. I'm not sure what that word says there. And your sample goes in here, and you press the button, and it measures the absorbance. Or we can measure transmittance, so we can measure the amount of light absorbed or the amount of light transmitted. Generally in chemistry, we're going to measure absorbance. So a concentrated blue solution is going to have a high absorbance, and that's quite nice because that means that absorbance is directly related to concentration. So the higher the absorbance, the higher the concentration, whereas reverse if it's transmittance. Colorimeter. Okay, we could make, or it could be a reaction where a precipitate is formed or used up. So something that is opaque, i.e. light can't get through it, becomes transparent, so light can get through it, or something that's transparent becomes opaque, so light can't get through it. And the classic example of that is the clock reaction here with thiosulfate and hydrochloric acid, and they react together to release sulfur. Sulfur is a precipitate, yellow precipitate, and you put a cross on underneath the beaker, and at a certain point in time you cannot see the cross anymore. Okay, that would be useful for initial rates measurement of rate of reaction. You wouldn't be very easily be able to measure that in a continuous fashion unless you put your solution in a colorimeter and you measured the absorbance over time, and then you'd be able to get the continuous measurement. Okay, but if it obscures across and you're just timing it to obscure the cross, you've just got a single measurement which will use as initial rate reaction. Okay, we could have a gas being produced, and there's a nice picture of gas bubbles being produced. They come out of the syringe. And in this case, what you're measuring is you're measuring the production of a product, but you're still going to measure the rate. Okay, so if you measure the gas, you're measuring the production of a product. You could, if the gas that you make is heavy enough, measure the mass. So if you had an open conical flask and let the gas escape, then the mass would decrease, and therefore you could measure the mass of the reactants decreasing. Okay, that's not going to work for hydrogen because, yes, that's right, hydrogen is too light. Okay, you're not going to get a very measurable mass loss on a laboratory balance that's only either 2 decimal or 3 decimal places. You have to have a much more accurate one and much more expensive. So using the colorimeter, okay, so read page 13 to 14 in your textbook, and then you've got a big note up there. You have the Caboodle version of this. Remember, you were sent an email. So what I'm now going to do is I'm now going to hide the presentation, and you should see Caboodle. Or have I been logged out? Looks like I've been logged out. Okay, so let's go back to Caboodle, which is here. Back to the home page. I might have to log in again. Save preferences. No, it looks like I'm logged in. Okay, so let's go back to the book. So this is Caboodle. You log in, and the instructions on how to log in are in the email you were sent. Okay, and I'm going to look at the digital book. Okay, and here is the digital book. We've got the biology ones. Well, I've got access to the biology ones. You probably have as well. But I've also got chemistry. Okay, so I've opened the Year 2 chemistry book. Okay, I'm on the right page. Oh, remembered that. That's good. Okay, so here is the explanation of how this works. Let's hide something else. Something else is getting in the way here. Let's move that over there. Right, so here is the book here. Okay, So monitoring the rate with a calorimeter, okay, it says read pages 13 to 14 in the textbook. So let's do that. Okay, so monitoring by gas collection, monitoring by mass lost. Okay, in a calorimeter, be very careful how you pronounce it. In a colorimeter, the wavelength of light passing through a colored solution is controlled using a filter. The amount of light absorbed by a solution is measured. There we go. And then you've got figure 1 there. It measures the intensity of the light. I should probably move myself. Where am I? Let's move on in a minute so we can see what's going on there. Okay, so we've got the colorimeter there. Ours look a little bit different than that. We've got quite nice simple black ones which are easy to use. A colorimeter measures the intensity of light passing through a sample. Filter chosen so it's complementary colour to the colour being absorbed in the reaction. So for instance, copper sulfate is blue, so you need a red filter. Iron oxides or iron 3 compounds are generally reddy brown, so you would use a blue filter. Absorbance is recorded, which is directly linked to the concentration of solution. That actually, if anybody wants to know, is called the Beer-Lambert law. Beer-Lambert, B-E-E-R. Okay. Right, so analysing. So the equation for the reaction of propane and iodine in the presence of acid catalyst is shown below. Iodine is orangey brown. Okay, so therefore, what colour filter would you want? Yes, that's right, you want a red filter. As this reaction proceeds, iodine is used up and its orangey brown colour fades. So the absorbance of the colour is measured precisely by the colorimeter. So in this case, this orangey brown colour gets less. So that means you're measuring the concentration of this reactant, the iodine, and it's going to get less as the reaction proceeds. Okay, and so therefore you get less and less absorbance, more light going through. And what you would need to do in order to work out the concentration, because there's this direct relationship between concentration and absorbance, you would need to produce some standards where you have some known concentration of iodine, some IT2 down there. Okay, so if we move on to the next page, you can see we would do this and we'd have our known concentrations here of iodine, and we'd measure the absorbance for each of those known iodine concentrations. And that means then that we could then, at different times when we're actually running the reaction in the cuvette, we could then take at a certain time, we could take the concentration, take the absorbance, read off across this graph. So let's have a pen. So you would take your pen, okay, so I had at time 10, I had, it's going to be quite a high absorbance to start with. So at, say, after 10 seconds, the concentration, that should be a straight line, but it comes across there. You draw a line across here for what your absorbance is that you read at 10 seconds, come down, mark an arrow, and you read off your concentration on there. Okay, and then say at 30 seconds, the absorbance might be down here, so you come down here and you read that one off. Okay, so therefore you end up with concentration against time. Okay. So what else did it say? Let's hide the pen now. So the pen. Just have a cursor. Okay, right. Okay, so cursor. So selecting the filter, complementary colour. So 0 the colorimeter with water. So before you actually start the reaction, you would need to put water in, which is going to be transparent to light. Okay, so you know you're going to get no absorbance with water. Okay, so you 0 it, and that makes sure the calorimeter is set up properly. Measure the absorbance reading to the standards, and you plot this calibration curve, and then you carry out the reaction, and you take the absorbance at different time measurements. So we could say that's like 10 seconds, as I said. Oh my God. And this might be, say, 30 seconds. Okay. And then you would carry on and use that to measure the concentration at each of those times. Okay, and then you would plot a second graph of concentration iodine against time. Okay, so let's come back to the presentation. Let's turn the book off for a moment, and let's move myself back to a sensible position. Whoa, that's the presentation. There we go. Right, okay, so That's using the colorimeter. So you should make some notes on that. Okay, and you had a worksheet where you did similar sort of experiment with bromine. Okay, so we can determine the rate using the graph. So we've got concentration on the left, on the y-axis, and the time on the x-axis. Now the time is in this case in minutes, but normally we probably want them in seconds. Most of the reactions that we do in the classroom are going to be measured in seconds. They might take, say, 6 minutes, but you'd have to convert that into seconds. Okay, so here's our reaction. A plus B makes C plus D. Concentration of B, so this graph is with respect to B. Okay, so it's measured every 200 minutes. Okay, so the rate at a given time we get from the gradient of the tangent, which you talked about last time. Steeper the gradient, the faster the rate. Place a ruler on the outside of the curve and draw a line, which you've done before or in the last lesson. And then you do y over x. So here is this graph here. This is taking at time 400, so at 400 seconds. Are we talking minutes or seconds? Yeah, really slow reaction. So 400 minutes, okay, and the gradient, the tangent line has been drawn. Notice how, if you look, try and get these tangents, because there's going to be leeway in the questions when you answer this, when you're working out a tangent. But if you try and look at this carefully, when you're trying to put a tangent on, the angle here and the angle here should be pretty much the same, okay, for you to have drawn a decent tangent. Okay, so you're going to need to practice doing that on paper. Well, at the moment, because we assume the exams next year will be on paper. But you could do that. You could also do it in Excel. Excel you can work out the slopes of lines. So here we've got the concentration, and we've got the concentration at 1.2 moles per decimeter cubed. Okay, 1.20 moles per decimeter cubed. So we've come across and we've drawn the tangent at that point. And we've got that's also at 400 minutes. Okay, but what we then need to do is to work out the gradient. We need to work out the slope of that line. Okay, and we're doing that by looking at the fact that it's approximately minus 1.6 moles per decimeter cubed, and it's approximately 1520 minutes, or for that to happen. Now that triangle here, so the triangle has been drawn. Where's my cursor? Here's my cursor. Where's it gone? Okay, so here's my cursor. That triangle, you can use it crossing the y and the x axis to work out your y and x coordinates, okay, because this gradient line does that. Okay, so I can see that it's gone from 0 to 1520, okay, and it's gone up to it's gone down because it's going down, so it's minus 1.6, and we get our rate being a decreasing rate of minus this, okay, and we've got the units. We've got moles per decimeter cubed, minutes to the minus 1, because minutes is underneath here, so it's minutes to the minus 1. Okay, so it's slowing down. Okay, so we're going to put this one up now. So sulfuryl chloride, SO2Cl2, decomposes to make sulfur dioxide and chlorine gas. The concentration was measured over time. Okay, here are the concentration values and the time in seconds this time, so that's in seconds. And so now you should draw a graph of concentration against time and use the gradient to measure the rate of reaction at time equals 0 and time equals 3000. Okay, and then we'll need to think about how the change in the sulfuryl chloride was measured. Okay, so what we should do is stop the video now. Stop the video now, and then we'll continue. Okay, so let's have a look at how we do that. Well, first of all, a gas syringe, because we're getting twice as much for every 1 centimeter cubed of gas that you have, the products is doubling. Yeah, so an overall increase of volume of 1 centimeter cubed for every centimeter cubed of sulfuryl chloride being used up. Okay, so we can measure the amount of sulfuryl chloride being used up because the gas is going to be produced. So if you use a gas syringe, it's going to get increased. And now I will move over to Excel and show you the graph in Excel. Let's see if this will come up. There we go. Okay, so here is the graph. Okay, so here is the graph in Excel. Okay, so there's a few things I want to just brush up on some graphing skills as well. Okay, so here is the sulfuryl chloride in moles per decimeter cubed. Okay, we can do some little fixing, can't we? We can do things like, if I go to that, okay, let's be a bit professional. Let's make that be, that should be superscription there. Click OK, and now you can see that actually is superscript there. So what I had to do is I had to go into the formula bar, select the bit that I wanted superscript, click on this little arrow up here, which makes the formatting cells expand, and then I can make it superscript. Okay, so that's a bit cool. Okay, so we've got time in seconds. Okay, now notice that these are all to 3 decimal places. And oh, that's a little bit dodgy. What does this hash 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 symbol mean? Basically, it means that the cell width is not big enough to hold all that, the number there. That number should be 0.500 because we've done it to 3 decimal places. So what I can do is if I go to the top of this column here, and when I get this double-headed black arrow like that, I can double click. That automatically makes my column wide enough for the numbers that are in it. So whichever has got the most widest stuff in it will make it wide enough again. Okay, some other quick tips. So here we've got it as 3 decimal places. These little buttons here, bang, that makes it 4. And again, I've caused a problem. Or I can go back to 3, or I can go back to 2. Okay, and you can see that the graph automatically changes. So this, you should be able to put a chart in. Okay, so show how to label the axes with units. Okay, so let's go and do that. So if I right click, I can format the axis, I can change the axis, I can add minor grid lines, I can add major grid lines. So let's click on the axis again, click on the axis, add major grid lines. Okay, I should probably do that with both that there. Let's make it a bit bigger so we can see what we're doing, but not so I'm in the way. Okay, so there we've got that there. Now we can do things like, well, if I click somewhere on the graph, I can add chart details, but also up here I've got design. Okay, and if I click, so this is in the main version of Excel. It will be different if you're using Google spreadsheet or the online version of Excel, which doesn't have quite so many features. So I can add some chart headings. So let's add the primary horizontal axis. So the primary horizontal axis is the time. Okay, so let's type in here time, and that's in seconds. So we put seconds. Okay, hang on, what happened there? Let's try that again. Axes, primary horizontal. Let's get rid of this. I don't actually want the key, so I'm going to get rid of the key. Right, let's try again. Let's do axis titles might help actually. Yeah, axis title will help. So primary. Okay, so the primary title, I can double click in here, delete this and put time bracket seconds. Oh god, spell properly. Right, okay, so there's time. Okay, and I can add the primary vertical axis. Okay, and double click in there, delete what it says there, and this is concentration. So square brackets, SO2 CL2, close square brackets, and that's in moles dm to -3. I think I should be able to, if I select that one there, I should, if I right click now, I should, right, I think I'm going to try a little tricky technique. Okay, I'm going to press Control Shift and plus. Yep, it worked. Okay, so that Control Shift plus is a quick keyboard shortcut to get a superscript. and if I select that 2, well, let me just select the 2, it should do. Let me put my cursor in front of the 2, select the 2 there, and put some spaces in. Okay, so put a space in there. Okay, and I'm going to put a space in front of the S. Come on. It didn't work. Let's put an S there. Yeah, go back. Right. There we go. Right, let's see if I can now just select the 2 by itself. Annoying. Okay, but I should. That's annoying. It's not letting me do it. Anyway, I could do Control and plus key, and that would make it a subscript. So if I wanted to make that properly right. Okay, so I've got those in there. Okay, so I've done this one. Yeah, how to label the axis with units. Now let's go back. We've got the chart again. So design. Let's add a chart title. So let's put it above the chart. Okay. Let's call this rate of decomposition. So, rate of decomposition of SO Control plus 2. Don't like it. Okay, so you have to leave it as SO2. CL2. Okay. Okay, so that's sort of a decentish title. Okay. Okay, so there's my graph there. So I've done that. Now we can now put in a trend line. Now to do that, first I'm going to make the graph a little bit bigger. Okay, to try and make the shape look clearer. And in fact, one thing we can do is I'm going to move the chart. I'm going to move it to its own new sheet. So let's have a look at that. So let's just recap what I did. I right clicked on here, somewhere here on the main part of the graph, not on a specific point. So not on a point on the graph, not on the axis, not on the titles, but in a space, and not there on the actual grid lines. It must be somewhere up here would do. And I can go move chart and put it as a new sheet. Click OK, and then I've got my new sheet. And now we can sort of see this is starting to look, it's bigger, and let's just make it actually a little bit smaller because I'm in the way. Okay, let's make it smaller for the moment. Let's move me up that way. Let's drag the window up. Spreadsheet. There we go. Let's see this stuff there. Okay, and then let's put me back down here in the corner. Maybe this baby in the corner. There we go. Right. Okay, so on the here, I can right click on a point and I can add a trend line. Now, hopefully, we should. Let's make this a bit smaller so we can see it. There we go. Right, so when I clicked on that, I can add a trend line. Now the trend line is various forms. Okay, we need it to be exponential. There we go. We've got a nice exponential curve because we've got the hopefully this is going to be like a half-life curve. There's my line on it now. This is looking pretty decent. I could print it out as a whole A4 page. I can do things like here for the outline of this. So I clicked on the line, the trend line. I can change its color. So let's go red. And also, if I check on there, I can have it a stronger weight. So perhaps if I go red like that, stronger, and dashes, or we can have it as a solid line. It's probably a little bit thick now. Let's make it less thick. So let's turn it down to say that. Yeah, there we go. So there is my graph now. And I would be able to put trend lines on that. I could do that manually by going insert and shapes. And I can draw a line like this, and I can draw lines at certain points. So say if I want to get the tangent here, I could draw it like like that. There's my line there, and then I can move it around a bit. Might want to twist that up a bit. I think that's probably better. I'll move it down there. So there you can see I'm almost got the same angle here and here. So there I think is my trend line, and of course then I could lengthen it, okay, or draw a triangle on it. Of course I could draw a triangle using this here. I need to find a right angle triangle, or in fact I can just change the angles on this. So I can draw a triangle, and then I can move that to make it a right angle triangle, and I could do all that sort of business. But I can actually put, I could even put, I could find the gradient of this line if I wanted to. Okay, but you can figure that out. Okay, so there's our graph. Okay, I'm not going to save that. Okay, so let's put the presentation back up. Okay, so we've got our graph in Excel. So here is my a version of that that's been plotted. Okay. You can change the colour of the grid line so it looks like proper graph paper. So the blue line is my main graph line, okay, my trend line that I put on there, which is an exponential line. And then the question asked about finding the rate at time 0, okay, and also at time 3000. So the red line is the one for 0, and the green one is the one for 3000. So the red line is fine, okay, because it crosses the x and the y axis. I can see a triangle on it, okay, so I can see that it's gone from 0 up to 0.5. Be careful that your x and y axis start at 0 if that's the case. So it goes up to 0.5, and it goes so it's dropping by 0.5. And also it has increased along the x-axis up to about 3,300 as measured by that line there. So we can work out our rate. Yeah, okay, this is the initial rate. Okay, the green tangent is t equals 3,000. So what's the rate there? Slightly hard to work out because it doesn't cross the x-axis. Okay, so you would need to draw a triangle. Okay. So here, if we get it to go to 4,000, so what you need to do when you're trying to draw a triangle on these on these tangents is try and make it so that they actually cross a nice even point. So here, that's hitting there at 4,000. We're starting at 0. So at least this bit, the 0 to 4,000, is a nice easy measurement to read off of the graph. So that's 4,000. This one up here is a bit more complicated because we're starting here at 0.14. Okay, and going up to about 0.38. Okay, so the change in the y is 0.38 minus 0.14, and the change in the x is 4,000. Okay, so we've got our new rate, and you can see the rate is smaller. Okay, -4, -5. Take care with your indices. So this is a slower rate. Yeah. Okay, so the rate it's decreased. Okay. So when we do it by graph, we can get tangents. We get tangents at different points on the graph, okay, and they're calculated. Okay, so what do we say there? The tangent at 0 time is used to calculate the initial rate. So sometimes we just do an experiment to a certain set time, and we then draw or we work out what the rate is there. Yeah, and we just use that time. Yeah. So first order and half-life. So example is radioactive decay. Okay, it will take something the same time to drop to a half of the original concentration as it takes to drop to the next half. So so half of a half is a quarter. So it might take a certain amount of time to get to a half, and the same amount of time to get to a quarter, the same amount of time to get to an eighth, etc. Okay. Right. So here we have a look at that. So A falls as the reaction progresses. So this is going from concentration of 4 at the start to 2, okay, and it's taken 17 minutes, okay. Then if you look at the next 17 minutes, it's gone from 2 down to 1, okay. So at time 17, yeah, here it was at 2 moles per decimeter cubed, and then at 30 times 34, i.e. 17 minutes later, it's now 1 mole per decimeter cubed. This is a nice one that is obviously going perfectly for half-life. Okay, then it's dropped to half mole per decimeter cubed in another 17 seconds. So the half-life is constant. So if you're trying to find out if the half-life is constant, you need to draw at least three measurements on there to show half-life. And they don't necessarily have to be from 2 to 1, then from 4 to 2, from 2 to 1, 1 to 0.5. You could go from 4 to 2, might be easy to do, but you might then go from 3 to 1.5. Yeah, and that should also, so from here, 3 down here to 1.5, which is around about here, is also going to be about 17 minutes. So they don't have to be, going down half each time. You could make it going from different half points, so from 3 to 1.5, from 2.5 to 1.25, yeah, along here. Okay, and it should be the same. Okay, so this is called exponential decay. Okay, we've got constant half-life. Examples obviously said radioactive decay using carbon dating. So the older something is, the less carbon-14 it will have in it. Okay, but that only works for a certain amount of going back in time, because of the carbon. You get to the point where the amount of carbon-14 that's left is so little that it's very hard to tell the difference. So that works for a certain going back in a certain amount of time. Okay, biological half-life, time for a substance to be removed from the body. Okay, so for instance, I'm probably suffering, well, actually I'm not too bad actually at the moment, of hay fever. That means my body's producing histamines when it shouldn't be. And obviously, if I want to try and control that, I have antihistamines. Histamines are produced, and then they should be broken down in the body, and the half-life is how long it takes to do that. For physicists, if you've got a capacitor, which is two plates which are insulated from each other, you can store charge on the plates, and that will then can discharge. Holy grail for electric vehicles would be to produce an ultra capacitor, because the thing is, a capacitor can pick up charge really, really fast. So if you put a voltage across the capacitor, it will store the electrons on it really quickly, but then it will then release those electrons to make electricity flow through your devices, but it discharges quite quickly. Some people are looking at making ultra capacitors, which would be an alternative to having batteries in electric cars. In fact, some cars now they use ultra capacitors as part of regenerative braking. Okay. Yeah. Okay. So let's have a look at the textbook, page 16. So there's this question here. So let's move to the textbook. Okay, and let's find the presentation in a minute. So page 16 in the textbook. Let's get to that. Okay, so what page are we on now? We're on. Right, on page 14. So page 16 in the textbook. Okay, so page 15 talks about half-life and goes through that as well. So you can see down the bottom here it's labelled as tier half. Yeah. Okay, so page 16. Okay, so what were we talking about here? We were talking about half-life. 16 textbook. Okay, yeah. Now, page 16 in the textbook talks about this. Yeah, very useful relationship, that the rate constant k times t1/2 equals log 2. Because this is a half-life curve, yeah, it's a log 2 log to the log 2 curve. Okay, that number log 2 is 0.693, so you can remember either log 2 and work it out, or actually remember that it comes out as 0.693. And this is a very useful way of doing it, because I could work out by doing tangents. Okay, so tangents to the curve. Okay, but that, as we've seen, getting a tangent exactly right is going to be tricky. So in the book, so let's find the presentation again. So in the book, we have got an explanation of this as well. So it's much easier. Let's show you. Let's hide. Move it out of the way. Right. Okay. So calculating the rate of constant and half-life, much easier way of calculating it is to use the exponential relationship for a constant half-life. So k is log 2 over t half, which we can rearrange to be t half times k equals log 2. Okay, or you can work out k from that. Yeah. Okay. So yeah. So read through this page. Okay. Good stuff. Okay. I'll keep the book open. Right. Let's move back to the presentation. Okay. So, this is really important. That's why it's highlighted in the box, and it's a quick way of doing it. So we found out from the graph that the half-life is 17 minutes. Now, if it was 17 and 16 and 18, you had some sort of variety around that, you could take an average of the 3 and call that your half-life, and then you'd be good to go. Okay. If it was 17 and 20, and then perhaps say 15, then it's a little bit iffy. Yeah. So if they're about 17, around about 17, and call it 17. Okay, so here we've got that worked out. So we've got the half-life is t half is 17 minutes. We pop that into the equation, or just rearrange it to get k by itself, and we end up getting the rate constant. Okay, and that is constant for that graph. Okay, that is this thing that the rate is changing. Yeah, the rate is changing, but k, the rate constant, isn't changing for this graph. Okay. Later you'll see how we can work out k in a slightly different way. Okay, right. Okay, so the rate constant we found by rearranging the rate equation. The value of rate would need to come from the calculated gradient of the tangent drawn at specific concentrations. It's always difficult to get the tangents right, so using k times t half equals log 2 is much more accurate. So now we're going to have a look at the booklet. Okay, so the booklet is on OneNote, and you're going to complete the graphs for this in your booklet. So let's have a look at where I've got that. I think that is on my, so let's hide the book, hide the spreadsheet, hide the presentation. There I am. And let's show my screen. Okay, so I'm going to go to the booklet, which is here. Now this is my class's booklet. Now the booklet is under booklets for you. I've moved it off to one side because I don't want you to show the names of the people in my group. So in the booklet, which is online, now actually I'll go up to the top of this. So here is the booklet. It's all in one page, but there's also a file copy of the booklet. And that's a Word version of the booklet. It has got some macros in it. There's a nice little button at the top which takes you to the periodic table, which is at the end of the booklet. And there are boxes in it for you to actually write on it electronically, which are quite helpful. And the same is true with the online version, yeah. So on OneNote, so here you can actually start typing in stuff in here. So if I click there, I will then be able to type my answer in here. I can't know what the answer is there, but I'll make a right rubbish in there. Yeah. Okay. So I can type something in there. Okay. Let's undo that. Okay. So that's 18.1. So the stuff you did in your last lesson. Okay, so there's space, so you click on the answer and you can type in your answers all there. Okay, and then it's online and we can all see it at the same time. Okay, so here we're looking at concentration time graph. So here I put the instruction to draw a drawing in this box. Okay, okay, so if I go up to the bit here where it says draw, I get draw and I can draw lines. I might have to move this over a little bit so we can see the lines. Okay, so I want a pen. Okay, so I'll take a pen and I might draw it in blue. Please only draw within the border, but yeah, I can't draw. Yeah. So draw a zero order. So here I'm just going to draw my line. Okay, with the mouse. It's not too bad. Okay, so zero order. What shape is that? So concentration aside here, time along here. It's going to be doing that. Okay, it would be a straight line. Okay, with a constant gradient. Okay, so that is the book that you can work on that, and you can do that online, and that seems pretty reasonable. Okay, so let's move back to the presentation. Okay, so the idea is that you complete that in your booklet, and it should end up looking like these pictures here. So zero order, first order, second order. Zero order, you should draw a graph like that, which I'll start to show you. And you can add in here. So the concentration decreases at constant rate, straight line. Okay. and the half-life decreases. Yeah, okay. This reaction has no effect on the rate, but gets used up in the reaction. So it's being used up, okay, because the concentration is going down. If it was a horizontal line, okay, that means that actual substance is not getting used up. But because it's going down, it is getting used up, but it's using up at a constant rate, okay, and it has no effect on the rate of reaction. Okay, the half-life is decreasing. We'll see that in a minute. Okay, so first order, we've got this shape, okay, which is our classic decay curve. Okay, constant half-lives, concentration halves, the rate also halves. Okay, and then we've got second order. Now this one, the concentration is decreasing rapidly. The half-life is getting shorter. Okay, so it loses half the substance in a certain amount of time, and then it's actually losing the next half lots of substance in quicker time. So the rate reduces by a quarter. So half-lives, the half-life is getting longer, but the amount of stuff left gets much less quicker. So let's have a see that. What can you tell about half-lives and rates? So half-life, time taken for the concentration is reduced by half. Work out at least 3, okay, and that will tell you the order. If the half-life is approximately the same each time in those 3 times you've worked it out, then you can say what the half-life is, okay. And we've said here, so we're going back to this and sort of seeing how this works. So the half-life decreases with time. So here, okay, in the 0th order, so we've got our initial amount here, we've gone down to half, okay, that's taken 800 seconds, but then that's continuing to, the rate is constant, so therefore this half-life is shorter, okay, it's going to be half, so it'll be 400 seconds to get to the next half, okay. Now in our half-life one, we've got this constant, so it's 200 each time, 200, 200, 200, okay, and so the half-life is 200 seconds, okay, and that would enable you to work out the rate constant. Now, in this one, to get down to half, the concentration is so fast to start with that you get down to half very quickly. Then it gets slower to get down to the next half, and slower to the next half. So if it took 5, then it takes 10, and it takes 30. So the half-life is getting increasing with time. Okay, right. So now, what we want you to do is to complete the past paper, which is on question 17 in your booklet. Okay, you will need to work out half-lives to get full marks. Remember, you need to do at least 3 half-lives. You need to work out the rate equation. Okay, assume that the methanoic acid is 0 order. Okay, don't forget units for anything. They won't give them to you in year 2. You'll have to work out them. And then we'll start on page 16 on your booklet. So let us put up this. Stop the video now. Stop the video now. Okay. And in fact, I will just show you the booklet. So let's show the booklet to just bring. Don't want that one. Don't want the presentation. Oh yes, I know what I'm doing. Right. So yeah. So here is the booklet. So read your textbook page 13 to 17 to complete that stuff there. Let's scroll down. Let's get rid of the. I'm just going to get back to the normal input rather than pen. Right. Okay. So let's just. Okay. So scrolling down. So what are we, page 9. So we're on. Right. So we've done that. Right. Page 17. So we're checking page 17 in your book. So this is the part exam question. So aqueous solution, methanoic acid, HCOOH, react with bromine. Student carried an investigation on the rate of reaction. The student used a large excess of methanoic acid. That meant that the concentration was effectively constant. Okay, so we're assuming that the methanoic is 0. Bromine is orange, becomes less intense, so colorimeter is used. Okay, and we can see the concentration of bromine is decreasing over time. In this investigation, a large excess amount, yeah, so it's 0 order. Using the graph, determine the order of reaction with respect to bromine. So you're going to need to draw half-lives on here. So, okay, let's flip back to the pen. Okay, so we've got green. Okay, so here, if we start at 10, okay, go down to here. So that's 1 half-life. So it's down here is 200. Okay, we could go from 8 down to 4. So 8 starts here, and 4 is here. Okay, so that's moved on, so that's also 200. Okay, so it's looking like it's about 200 seconds. We'd need to draw another one, so let's actually do from 4. You know what, I should do these in different colours, pens, shouldn't I? Yeah, let's just go red. Okay, so 4 down to 2. Ugh, went black, never mind. That's weird. Okay, so that's going from here to here, which is 250 to about 450. So again, 200. So it's working out, it's about 200 seconds. Okay, so let's go back to. So you should be able to answer that question there. So yeah, so in your answer, make clear out the conclusion. So you can type in your answer here, using the graph to determine the order, using the graph to determine the initial rates. Okay, so you need to draw a tangent on it, calculate the rate constant. The reaction will be method under these conditions. So try calculating K using the half-life. Do you get a similar answer? So that's where you need to use K equals what we're doing. We get log 2 over t1/2. Yeah. Okay. Right. Let's close that now. Okay, and come back to the presentation. Okay, so let's get rid of stop the video now, because you shouldn't be stopping the video anyway. So the answers. Okay, so let's go through the answers. So and let's actually go to the presentation. Show the presentation. There we go. Okay, so 2 half-lives measured. Evidence of 2 half-lives is points, but really I would say 3. Any half-life stating, so we said 200, which is smack in the middle, or saying a constant half-life. Therefore, you can state its first order. That is the only correct response. Okay, so if you didn't get the half-life to be 200 or to be with pretty much within that range, and saying it's the same at each time pretty much, then you would be wrong. You could get that mark if you had written down the rate equation as rate equals k br squared to the power of 1, or rate equals k br squared br2. Note that you don't necessarily, because it's a first order reaction, you don't have to write the 1. Yeah. Okay. Tangent needs to be drawn at t equals 0. Okay. And therefore you should then be able to work out the rate, okay, from that. Okay, units should be in moles per decimeter cube per second. Okay, and in the last lesson you were shown how you could check that. So rate is that. Okay, and the calculated rate is going to give you K. Okay. Okay, and K will have units of seconds to the -1. Okay, so activity page 16 in the booklet. Complete the task investigating the effects of concentration on rate of reaction on page 16 in the booklet. You'll need to finish this part of your homework this week. Okay, so that's page 16 in the booklet. Although it said take graph paper with you, you can't take any graph paper. We're not going to mark any graphs, because if we did, we'd have to have them in a box for 72 hours before we could look at them. But you can do that on Excel, which we've shown you how to use. Okay, so here is your task menu. We're nearly there. Okay, so finish up the questions in your booklet, page 15 to 18. The textbook, pages 13 to 17, answer the questions. That's pretty much it. Okay, so let's just recap. Remember that those are medium and straightforward tasks. The red one is the straightforward, so everybody should have done that. Medium, pretty much most everybody should do that booklet as well. Okay, so that's what we've gone through. Concentration time graphs for experimental results. Continuous monitoring of rates. Okay, rate of reaction and concentration time graphs. Calculating half-life from a first order graph. And the rate constant from half-lives. So here is an additional question that you could have a look at as extra work. Okay, so those are the questions here. I'm going to stop the video now. Okay, sign up. Okay, and probably should move it some or make it a bit smaller so you can see it. Stop the video now. Okay, and then in a second I will carry on and go through the answers. Okay, right, hopefully you can read those questions. Okay, so let's go through the answers of those. Okay, so the answers are K equals that, rate equals the ester times the hydroxide. So let me just go back and have a quick. So rate of decomposition of dibenzene carbonyl peroxide is first order with respect to peroxide. Calculate rate constant for this reaction at 107 degrees C. Note that temperature is important. The rate of decomposition for the peroxide is 7.4 when the concentration of peroxide is 0.2. Okay, so yes, I will demonstrate that. Okay, so okay, let's put the visualizer on and make it a bit bigger. Okay, so we have got a rate equation. How am I going to do this so I can write right around? That's better. Rate. So rate of decomposition is first order with respect to the peroxide. So rate equals K peroxide. There we go, rate equals K peroxide. Okay, so what do we know? Well, we know that that is 0.02 moles per decimeter cubed. We know that the rate of decomposition here, this is 7.4 times 10 to the minus 6. Okay, so to work out K, we need to do 7.4 times 10 to the minus 6 over 0.02. And that comes up with our answer. Okay, 3.17 times 10 to the minus 4. Yeah, that makes sense. I'm thinking about this. Does my answer make sense? I haven't actually put it into a calculator and worked it out and to check that that's right with what we had on the presentation. But I know it makes sense because I'm dividing by 0.02. Okay, so when you divide by a smaller number, the number's going to get bigger. It's gone from minus 6 to minus 4. There's a factor of 100 in there. That makes sense because it's going to be minus 4, so I know I'm in the right ballpark. And in fact, yeah, actually I don't need a calculator. Idiot, do I? 7.4 divided by 2 is 3.7. Yeah, so it does work, yeah. So it didn't even need a calculator. Okay, so the next one is that rate equals K ester hydroxide. Okay, so let's just go and check that. The hydrolysis of the ester methylphenoate in alkali is first order with respect to the ester and first order with respect to hydroxide ions. The rate of the equation is that at a given temperature when the ester concentration is 0.5 and the hydroxide concentration is 0.10. Okay, so let's make this bigger again. Okay, fresh paper. This is a pen that's been neater. Right, so rate is first order with ester, so we can write rate equals, so we've got the ester and we hydroxide. So remember, the square brackets are the concentrations. I could write ones here, but I'm not going to bother because they're first order. The rate of reaction is that. Okay, so let's just check that answer. Yeah, rate equals K ester OH minus. Okay, and then the next part of the question is to calculate the rate constant K. Whoa, forgot to put K in. Okay, there's K. Right, okay. So now we need to work out K. So I could rearrange the equation first before I put anything in. So I'm going to get K is rate all over the ester and the hydroxide. So basically I've just moved those over to the other side. I'm dividing by them on this side, got divided on that side. Now I can fill in my values. So I've got that the rate of reaction is 0.00069. Okay, concentration of the ester is 0.05. Okay, times the concentration of the hydroxide, which is 0.1. Then I can work it out. Well, I'm not going to bother. I'm going to simply put the answer up. Okay, so put the answer up. Okay, so it's 0.138. Does that seem right? Well, I'm dividing by 0.1 there, so that's going to get rid of a 0. I'm dividing by 100 here, that's going to get rid of 2 zeros, so that's fine. Okay, and then I'm dividing by 5. 5 into 69 is about 13.8. Yeah, so 0.138 moles per decimeter cubed per second to the minus 1. Okay, so we've got moles to the minus 1 dm cubed. Yeah, okay, so let's just check the working out of the units. Okay, so we've got a rate of moles decimeters cubed seconds to the minus 1. Okay, and we're dividing by moles per decimeter cubed, one concentration, times moles per decimeter cubed for the next concentration. Okay, so seconds is going to stay, is not nothing's happening with that, but that cancels with one of these. Okay, so it leaves us with seconds to the minus 1 over moles dm to minus 3. Because it's one over the other, we can flip them up, so that becomes moles to the minus 1 decimeters cubed seconds to the minus 1. Okay, because there are the moles decimeter cubes underneath. Okay, so that's just a quick check on the units. Okay, so let's get rid of the visualizer. Okay, and I think that's it. Okay, thank you very much.